This video is the third lesson for Chapter 7, our electromagnetism chapter, and we're going to finish up the idea of using magnetic field to apply a force on an object. Last day we looked at a moving charge, how it could actually feel a force, and now we're going to look at the force that a current would feel in a wire if that wire was inside a B field. Same as last day, I'm going to start off with just a little review of what we know. You don't have to write any of this down. We know that permanent magnets have north ends and south ends. The magnetic field comes out of the north end and goes wrapping around and dives back into the south end. And if you're ever wondering which way the magnetic field is pointing in one particular place in space, just grab a compass, and it always points in the direction of the B field. So a compass is really just a magnetic field direction indicator for us. Now, it's awkward carrying magnets around all the time, so we saw on the very first day at the end that maybe a better way to go would be to use electric currents to make magnetic field. You can have a long straight wire. It does make a magnetic field that wraps around the wire, or you can, this works way better, make a solenoid, a coil of wire, much stronger magnetic fields, cleaner direction for them too, inside the core of the solenoid. And then last day we started off, got about halfway through this section here, the forces on moving charges and currents, but we only took a look at moving charges. And we found that the equation for the force on a moving charge was this neat right-hand rule, F equals QV crossed with B. And so you have to make that right-hand rule gesture in order to find the direction. And that only works half the time, because the other half the time, the Q might have been negative, and then it's the exact opposite way. Well, what we're going to look at now is, what about a wire with a whole bunch of electrons sliding along it inside a magnetic field? Each electron will feel a force because of that QVB, and that means the whole wire is going to get pushed around. So in a second we're going to get to this. Part 2 is going to be the force on a current in a B field, and it complements the idea of force on a charge, and it's also going to be a right-hand rule. So let's dive right into this. Here we go. Yeah, this is the part where you will want to actually start making some notes. Let's look at the force on a current on many charges inside a B field. Because a current really is just a whole bunch of electrons sliding along that wire. Okay, so I'm going to show you a picture here. Don't copy this for a second. Maybe I shouldn't have said, pick up your pen. Let's think about what we saw last day. Okay, here's a couple of permanent magnets with a north end on your left and a south end on your right, and the magnetic field comes out of the north end of one and into the south end of the other. And if you had a Q, like a proton or an electron flying along in that space, it's going to feel a force if it's got a velocity that's crossing that B field. And all I'm suggesting now for today is, well, what about a wire? Isn't that the same thing, right? Isn't it the same thing as a Q moving, right? It's just got a whole bunch of electrons moving along that wire, and it turns out it is. So now it's definitely time to grab your pen. Here's the equation. It's actually the exact same equation of QV crossed with B. It's just been manipulated around to calculate how much Q is moving in the wire with how much velocity. It's really the identical physics issue, just rewritten in a more convenient way. Okay, but it is fundamentally talking about the same thing. We just have to now modify our idea for which letters are which for the right-hand rule for putting on our fingers when we do that right-hand rule gesture. Last day we had V being our thumb because it was before the cross. It was QV crossed with B. Well, now the I is before the cross, so your thumb is the I. I like to think of it as it's the movement of charge, right? Whether it's a single moving proton or if it's a whole bunch of charge going down a wire, the I is just that movement of electricity. And then the B finger doesn't change, it's your pointing finger, and the force is always going to be your middle finger. It will work best if that current in the wire and the magnetic field that the wire is sitting in are perpendicular, okay, if they're beautifully crossed. If they're not perfectly crossed, then we can just go with the idea of I times B and the L multiplied by the sine of the angle between the I and the B. For the I, we're going to go with the traditional Benjamin Franklin current direction. That idea where you say, oh yeah, there's a battery, and I got a wire there connecting up the two terminals, and the current comes out of the positive end and wraps its way around towards the negative end. We all know that it's actually electrons going the other way, but for the math that we're going to do, that is mathematically the same as if there were positive charges moving out of the positive end. So we're going to go with the traditional current direction for the eye. You don't have to reverse anything around because it's electrons. It is actually electrons, which are negatively charged, and they're going the other way. And the two negatives kind of make a positive out of this deal. Two wrongs make a right here, so we'll actually be fine. Now, thinking about that right-hand rule gesture, last day we had this. The V was first in the question, the B was second. Well, now we've got an I and a B. So we're just going to make a change. We're going to change that thumb to be an I, and then everything from there is fine. The B doesn't change and the F doesn't change at all. Okay, let's try this deal out where we find some missing vectors, and then we'll do 3 numerical questions. The very first question, we're missing the force. There's some I, some current flowing off to your left, and there's magnetic field penetrating down into the screen. We're going to see if we can figure out which way that current would get pushed. Now, this picture is a little bit weird. Like, you look at it and go, what's this current? Well, maybe I haven't drawn it all in. Maybe there's a wire like this, kind of going from your left to your right, with current going off towards your left, right? So if you're looking at that thing going, what is happening with this? Think of it this way. So there's a wire, and it's in a magnetic field. The magnetic field's got all of its magnetic field lines going into the page, and you're trying to figure out which way that wire is going to get pushed. So you make that right-hand rule gesture that looks like this, and we'll line up what we know. You can line up your pointing finger into the page, and your thumb has to go off to your left. And while your thumb is going left and the magnetic field's going into the page, your force finger is going to be down. So this wire will get pushed down towards the bottom of the page. Down to the south, I guess, might be the safest way to say that. Okay, the next question. There's a force that's actually coming at us. It's coming out of the page. The magnetic field's kind of going to the south down there. We're trying to figure out which way is the current going. Well, take your right hand and maybe let's get your force finger pointing at you. And while your force finger, your middle finger is pointing at you, roll your hand around that finger until your pointing finger points to the south. And when you do that, you'll see that the eye also points off to your left. One final one. Which way does the magnetic field go in this story? There's a current that's going into the page. There's a force on that current that's going off to your right. Well, which way would the B have to be in order for that to happen? I'm going to take my thumb and imagine sticking it into my notes. That would be the green X. And then roll around my thumb until my middle finger points off to my right. I have to be using my right hand. And when I do that, my pointing finger points up towards the sky, up to the north. So there's a little game where we just find direction. Now let's do 3 questions where we go and find size. And we're going to take these 3 questions and we're going to go from easiest to hardest. So just so you are aware that the level of difficulty is going to climb on each one. First one, find the size and the direction of the force on a 12-meter section of wire. That's got a lot of current on it, 280 amps going west, and the magnetic field is enormous, 2.2 Tesla going to the south. Okay, first thing I'm going to do is try to figure out this direction. They said the current was going west, so I'm going to draw a westward current, and I'm going to connect them up tail to tail now. The magnetic field goes to the south. So you can take your right hand, your thumb has to point to your left, and while your thumb stays pointing to your left, roll around your thumb until your pointing finger points to the south towards the bottom of your paper. And when you do that, you'll see that the force finger, your middle finger, is coming at you. So this thing will actually be lifted up, okay, coming out of the page. Now, for size, we're going to go with LIB for this calculation, and it looks like there's a beautiful 90-degree angle in between west and south. So as far as LIB sine theta, it's going to be sine of 90. It's going to be the best cross product we can get. And just numerically, when you run all of those numbers, what you find is it's a very big force, 7,390 newtons, and it'll be coming out of the page. So that's the end of our first of 3 examples. Now they're going to get a little bit harder. This second example, I actually saw on an old provincial exam, right? On one of their download pages where you could download them and practice them. And they had like an L-shaped conductor, kind of like a carpenter's square. And you were going to try to find the force acting on it. Now there's a lot more information in the picture, so let's start adding some stuff here. In fact, I'll keep adding until it's at the point where you can like maybe pause the video and then be ready to solve it. They had magnetic field kind of bathing this whole thing. Let's have it going down into the page at 1.45 Tesla. So all of this L-shaped conductor is inside some magnetic field. Then they needed to hook up some sort of battery in order to get this to work. So they had maybe a car battery, 12-volt battery, with a 3.2 ohm resistor in there in order to limit the current. And a little bit more information, they gave you the size of this L-shaped conductor. 4 meters on one side, 3 meters on the other. And there are a whole bunch of little conceptual issues that you have to be aware of in order to solve this problem successfully. We need to know which end of the battery is which. The big line's positive, so the current's going to go counterclockwise. We need to know about Ohm's law to figure out how much current there's going to be. And then we can start diving into the electromagnetism. So the current with Ohm's law, 12 volts divided by 3.2 ohms is 3.75 amps. So we're starting to solve the problem here now. If you're wondering when did we transition from seeing this would have been the problem right there. They would have given you all of that. And now here's the solution. So we calculate the current, 3.75 amps, and that current's going to be going counterclockwise. Now, we can't just go LIB and use 7 meters because not all of those 7 meters have current going the same way. So we have to think about this section by section. It was a nice question they had on this old exam so that you could actually add up some forces using vectors with some Pythagoras. So in the first section, you've actually got current going up towards the top of the paper while the magnetic field dives into the paper. And that's actually going to create a force to your left. But then as the current goes around this upper section, the current will be going to your left. And if you have your thumb of your right hand pointing left, well, the pointing finger for B goes into the page, then the force would be down to the south. And we can find these two values. We've now got beautiful cross products, beautiful 90-degree angles in there. Force number 2 is going to be 16 newtons to the south, and force number 1, it's a little longer section, so it's 21 newtons, and it's to the west. Now we have to be careful. We don't want to just add them up and say, oh yeah, 16, 21, 37 newtons. Those forces are in completely different directions. Now we've done this many, many times, so I'm not going to bore you with the task of writing out all of the Pythagoras and the right angle trigonometry. Let's just put one little word in there and say, hey, Pythagoras, right? Pythagorean theorem would have to be applied here. And it's actually not 37 newtons, it's 27 newtons, and it would be 37 degrees south of west. So we've seen that enough that I think we can just make a little note there and go, yes, all right, that would be a two-dimensional force addition there to get that to work. And that takes us to our last question of the day, and probably the most challenging to try to draw and convey online here. Got two wires, they're both 8 meters long, and they're running parallel to each other, and they've got 24 amps of current in opposite directions, and they're 1.2 centimeters apart, okay, as they run parallel to each other. And it turns out they actually apply a force on each other because of the issue that we've seen today, because of LIB. So the hardest part of this is just drawing this. So this is me trying to draw two wires coming at you, right? I needed to get a little 3D perspective here. So the wires are running parallel and they're coming at us. And one of them has current going into the page and one has it going out. And it doesn't really matter which is which, but we do have to make sure we have them alternating with one in and one out. I'm going to make current number 1 go into the page and current number 2 comes out. Now these wires do feel a force, and it's because of LIB, and it's perfectly fair for you to look at that at this moment and say, well, yeah, there's a length of wire, 8 meters, and there's some current on them, 24 amps, but where is the B coming from? And the answer is they each make a B that the other one feels. So let's start off with, it doesn't matter where we begin, I'm going to begin with wire number 1 and say, imagine wire number 1 is doing what we learned about on the first day. It's a long wire and it's going to make magnetic field travel in a circle around it. So I would grab that wire with my right hand. I'd have my thumb pointing into the page to denote this current going into the page. And I would watch my fingers wrap around this wire and they would go in a clockwise direction, talking about my fingers. So the B field from wire number 1 goes like this, in circles around it. And as that wire circles around, that magnetic field, I should say, as it circles around wire number 1, it's going to pass right on by wire number 2. And as it passes by wire number 2, because the magnetic field is going in a clockwise direction, okay, that's that right-hand rule we saw on the first day, that one where you grab the wire like a fist, over where wire 2 lives, we're going to see that that magnetic field from wire number 1 goes down to the south. All along that wire, it's going to feel a magnetic field in that direction. And we could figure out how big it is if we knew how far we were away from wire number 1, that radius of the circle. But we do know, they told us that the wires were 1.2 centimeters apart, or 0.012 meters apart. So we could then go and apply what we've learned today. We could now go and do LIB. Wire number 2 has a current coming at you, so take your thumb, point it at yourself. It's in a magnetic field that's going to the south, so while your thumb stays pointing at you, roll your hand around, your right hand, until your pointing finger, your B finger, points towards the south, towards the bottom of your paper, and you'll see that your force finger does indeed point to the right. And if you're not sure about that at all, we can go over that online in the sessions that we'll do during the week. So it definitely will feel a force. And now to calculate how big, we just have to blend two ideas together. So we've got mu naught I over 2 pi r to figure out how strong magnetic field 1 would be where wire 2 lives. And then that is going to get inserted into this calculation of force that wire number 2 feels. So we'll just take that mu naught I over 2 pi r and drop it in right where that B is in today's calculation. Package it all together and we end up with an equation that looks like this. There's the mu naught in there, 4 pi 10 to the negative 7. The length of the wire, both currents, and then divided by the 2 pi r. So the calculation would be something like this. And it ends up being 0.0768 newtons. It's not very strong and it's repulsive. Now, wire number 1 feels the exact same size force, but in the opposite direction. It's going to feel a force off towards the left. And the reason why it feels a force to the left, well, there are two ways to think about it. One, the simplest way, is Newton's third law. If wire 1 pushes wire 2 to the right, then wire 2 will push wire 1 to the left. Easiest way to do it. The other approach would be to start all over again and think of wire number 2 as being the thing that creates magnetic field, and it would actually make a magnetic field that circles counterclockwise, still towards the south where wire 1 lives, and then apply LIB again. And you'll see that it does indeed apply a force off to the left, and we can go over that in the online sessions if you like. But that's the calculation. It does involve blending these two equations together, this mu naught I all over 2 pi r, and dropping that into this equation here, and to come up with then this big calculation, this blended equation that will let us see how much force there is. And that finishes up our second day for electricity and magnetism. Our third day, I should say, for electricity and magnetism.